course, are familiar with the map. And we are doing quite a lot of research on photonics in Europe. And in particular, last 5 years, we have been participating in the Network of Excellence, which one of the topics was devoted to the photonic liquid crystal fibers. And in particular, I'm from the capital of Poland, from Warsaw University of Technology. So it is the biggest technological university in Poland. This you can see the main building, and this very beautiful building comes from the end of the 19th century. And we have organized a lot of events related to photonics. I'm with Faculty of Physics, so it is a smaller building located in the campus. The campus is not so great as the campus here in Beijing Institute of Technology, but it's relatively nice. Some data about this faculty in order to place you in the situation. Faculty is relatively new, but the physics has a tradition for over 100 years at my university. So we are both, and initially with applied physics and mathematics, and the Faculty of Physics was established 10 years ago, the separate Faculty of Physics. I'm the Optics and Photonics Division Head, and there are two groups which are related to the, one is fiber optic photonics, so we are doing research on photonic liquid crystal fibers, and an optical processing. So a few professors, PhD workers, and a lot of PhD students and graduate students. Altogether, we form a group about 40 people related to optics and photonics. This is some view graphs of my research group in fiber optics from our faculty, some research topics. Some of them will be familiar to you after this set of lectures. And this is in particular the laboratory equipment experiment related to photonic liquid crystal fibers and to the photonic crystal fibers itself. As you can see, we have relatively young staff and PhD students, which we are doing a lot of also research on applications of different fibers in fiber optic sensors. Just coming back to the topic itself of my set of lectures, we have been collaborating within the topic of photonic liquid crystal fibers throughout more than 10 years, throughout not only in Poland, but also worldwide. I will just enumerate some people who are involved in the projects from our faculty, some recent PhD students. There are also groups which are very important for us who deliver liquid crystals, group of chemistry, military, University of Technology, and both faculties, Institute of Chemistry and Institute of Physics. And also the people who manufacture photonic crystal fibers for us from the technological group, Maria Curie-Skłodowska University in Lublin. There's also a collaboration, a long-time collaboration with a group in Canada, more than 20 years. Université du Québec, Ottawa, and the group in Singapore recently, and Belgium, and also throughout the network of excellence, the almost whole Europe. The outline of my today's talk is devoted to fundamentals of the photonic liquid crystal fibers. The second talk on Friday will be devoted to more specific applications and more specific phenomena. So today I will give you fundamentals, historical background. We will start with liquid crystal core and also modifications of elliptical liquid crystal core fibers which were predecessors of photonic liquid crystal fibers. Then a few words on photonic crystal fibers. I know that Professor Russell will give a set of lectures starting from tomorrow. So On Friday you will be more familiar with these fibers, but in order to continue my talk, some few basic information about photonic crystal fibers. Then also I will remind you some fundamentals of liquid crystal, and in particular of optical properties of liquid crystals, which are very important for application of photonic liquid crystal fibers. Then we come to the topic itself, fundamentals of photonic liquid crystal fibers. We will look for a variety of structures and variety of possibilities, and also some basic linear propagation mechanisms which will be addressed. The next topic, very important topic in manufacturing technological process of photonic liquid crystal fibers, will be devoted to methods of alignment. So one very important method is related to so-called photo alignment, so alignment by using the light. At the end of the 2 days talks, I will just say some basic physical properties and phenomena which are characteristic for photonic liquid crystal fibers. Thermal effects, external field induced effects, I briefly mentioned polarization effects, which will be discussed more in details on Friday, and some devices which we have constructed along the last few years. Today's talks will begin by some basic non-linear properties of the photonic liquid crystal fibers. So, from very beginning, it's a history. So, at the beginning of 90s, as you can see from these papers, the first discussion how to propagate the light without the fiber structures which are composed of the liquid crystalline cores. So imagine you have capillaries in the terms of dimensions of optical fibers, and optical fibers have dimensions in the range of hundreds of micrometers, so sub-millimeter scale, and inside these capillaries you put a liquid crystal and you try to propagate a light within the liquid crystal which is sustained in these capillaries, is surrounded by the glass. And from very beginning people discussed theoretically the situations when these liquid crystals form different orientations, and this is very important for further discussions. So we can distinguish so-called planar structure when the elongated molecules are situated along the fiber axis, z-axis, so oriented parallel to the z-axis, and both situations when the molecules are oriented perpendicular to the glass walls. In that situation we call this either radial structure or axial structure. This axial structure differs from radial structure in that sense that at boundaries the molecules are oriented perpendicularly. However, in the middle of the fiber they follow the long axis of the fiber. So these three types of confinement of molecules, liquid crystal molecules, were theoretically analyzed, and then first attempts to practically propagation has been undertaken. For the theory of optical fibers, the most important parameter is the so-called modifying frequency, frequency V, which distinguish the situation when we have a wavelength, light of a wavelength lambda, which is being propagated within the fiber, and we have dimensions A of the fiber core, and also we are related to two coefficients, refractive coefficients of the core and of the cladding. Cladding surrounds the core. In the theory of propagation in optical fibers delivered about 100 years ago in the beginning of 20th century by Hondros-Debye equation, we can differentiate different type of modes. Modes in the propagation, fiber modes, are the types of electromagnetic field which can be guided within the fiber. So they are transverse electric, transverse magnetic, or hybrid modes. These lowest order transverse electric modes can propagate only when this value, so-called cut-off frequency, reaches to 0.405. So in liquid crystalline fibers, so in this structure, when we have a liquid crystalline core surrounded by the glass, there is, as usual, we can distinguish propagation constants, which describes how the electromagnetic field is being propagated within this structure. And we can have a complex propagation constants, real and imaginary part, whereas real part of the propagation constants is responsible for the refractive index of the mode. So each mode has its own refractive index. We call it effective refractive index. However, the imaginary part is responsible for losses. So we have two phenomena. We have one is this field, electromagnetic field is being propagated due to this effective refractive index, and another, some of the power can be dissipated due to the losses of the imaginary part of the complex propagation constants. One of the most important parameters to characterize propagation of the light electromagnetic field within the fiber is so-called numerical aperture. Numerical aperture can be just derived from the theoretical analysis and can be related due to the special treatment. I just showed you only the results by comparing the refractive index of the liquid crystal core, so NLC, and different refractive index of the mode, effective refractive index of the mode. However, this numerical aperture derived from the propagation theory within the fibers, one of the Debye equations, can be very easily measured in the experiment. Imagine that you have a fiber and the light which goes out at the output of the fiber forms kind of a cone. And the dimensions of the cone give us the idea about the numerical aperture. So, in principle, there's one of the simplest experiments within the optical fibers to measure numerical aperture, just to observe the output cone of the light propagating within the fiber, and we can establish the experimental value. So, by this simple experiment, at the very beginning, about 10 years ago, we could observe propagation within the liquid crystal core fibers. And there's some data comparison about the different types of orientations, planar and radial orientations, and the theoretical data for these two types of orientations. These are different types of liquid crystals which were put within the core, and while these were compared with the data, it appeared, due to this simple comparison, that the liquid crystal form predominantly planar orientation. So when we put liquid crystals into the capillary, they initially form planar orientation. Planar orientation, so they will orient themselves due to flow within the liquid crystal core. And this was, as this device, these fibers, liquid crystal core fibers, have been tried to apply in to sense pressure, and this has been done with our colleagues in Canada, starting from the beginning of the 90s. And the data represents possibilities of liquid crystal fiber to sense hydrostatic pressure. This pressure region is relatively high, 6 megapascal or 60 atmosphere. This beating can repeat themselves as experimental data, and the initial experiment were performed for the capillaries, 15 micron capillaries, so 15 micron core, which were put in liquid crystal, special type of pneumatic liquid crystal. So, but some modifications of the structures within the liquid crystal core fibers was possible when the core changed their geometry from radial to elliptical. And these microstructures, elliptical liquid crystal core fibers, had very nice property. They can, due to special surface treatment inside the liquid crystal, into this elliptical core capillary, so in A and B, there was put a special substance. It was possible to orient molecules perpendicular to the long axis of the fiber. Due to the fact, and also due to the fact that the material used had very nice properties, that one refractive index along the elongated molecules was higher than the silica glass, than the glass surrounding glass, whereas another was lower. It was possible to demonstrate propagation of only one polarization, so only one field, which was just composed parallel to this long molecular axis. And this is evidence of a single polarization. However, single polarization, but also multi-mode. So we could have a lot of modes which could propagate only along the A-B axis. This was very nice achievement, and this fiber could be, for guiding this only single polarization, could be applied for very nice switching and also polarizing the light within the fiber. And this microtomographic view graph of these microstructures, elliptical core fiber. However, this fiber had relatively large attenuation. So while propagating a light within a liquid crystal core, we can propagate only for very short distances due to the high propagation. The propagation in terms of dB, 1 dB per 1 centimeter. In comparison with traditional fibers for telecommunication, this data is less than 1 dB per kilometer. So these fibers, light propagating within liquid crystals, can only serve for a short distances for changing properties of the light. That is why, and fortunately, appeared photonic crystal fibers, which could change the idea of using liquid crystal to merge with fibers in order to enhance propagation properties and also diminish attenuation. And now I will just give you some very basic and very short properties which you will have next lectures from Professor Russell, in various attitudes and various dimensions discussed. So, photonic crystal fibers, just as they are a kind of photonic crystals. So, if we have in order to obtain photonic crystal fibers, we should introduce a kind of defect in the regular structure of the two-dimensional photonic crystal. So, due to this defect, the light can propagate within this structure. And this defect can be, and this is a cross-section of photonic crystal fiber, and the dimensions of these photonic crystal fibers are kept typically for about 100 micrometers as standard fiber. We can have either a defect, a glass, so this can be another type of glass, or it can be also an air. So two types of defects are possible. So that is why so far there are a lot of types of different structures of photonic crystal fibers. We call with a glass core, so with solid core. We have with air inside, so hollow core, and some modifications, and also nice structure which will be discussed in detail by Professor Russell. For applications with liquid crystals, and also in general, we can distinguish two basic photonic crystal fiber types. We call it high index guiding and low index guiding. What is the difference between high index guiding and low index guiding? Difference is that high index guiding fibers have solid cores. So the core is a glass. And the glass has higher index, refractive index, than the surrounding silica. Silica glass with air holes. So if we have an average of refractive index of the cladding, so we observe when we have holes, air holes, and silica glass, so the refractive index will be absolutely lower than the solid core. So that is why we have high index inside, and the light in fiber optic mode will be guided similarly to a typical fiber when the index of the core is always higher than the cladding. However, there is also a possibility of low index guiding. Whereas in low index guiding, we have an air hole inside the fiber, surrounded by the structure of holes and the glass, and this effect is different than the standard fibers. And let us discuss in briefly mechanisms of the guiding. If we have a photonic crystal fiber with a solid core, so the light will be guided in glass. The refractive index of the core is higher than the refractive index, average refractive index of the cladding, and this mechanism resembles a mechanism of the traditional fiber when the light is guided by total internal reflection. Due to the presence of the holes, we call this modified total internal reflection mechanism. And you can see here, this is a cross-section of the refractive index profile. So this is a silica glass index, and this is in red is average between the silica glass and air holes, which have the refractive index equal to 1, and silica glass approximately 1.46. So we have higher index inside core, and that is why we guide the light due to high index or modified total internal reflection. However, when the this is also the same mechanism with a fiber from the view graph of the transition fiber. And look, when we have a modified total internal reflection, we can guide the whole spectrum of light. So all the frequencies of the wavelengths of the light could be guided within this fiber. However, when we have a fiber with an air hole, so surrounded by this cladding Corey structure, so we called the refractive index of the core is lower than the average refractive of the cladding, and in this type it is low index guiding, or the mechanism is called photonic bandgap. So the photonic bandgap mechanism relies by trapping a light within a low index due to the bandgap structure, which resembles the bandgap structure mechanism of description resembles the bandgap structure of semiconductors. So this will be discussed, I'm sure, in details by Professor Russell. And due to the fact you obtained only selected wavelengths, which could be guided within the fiber. So not the whole spectrum, but only selected wavelengths. And this is represented also schematically, this guiding, when we decrease the index, not this red line, but this dark line, black line, represents the refractive index of the core. So this is another mechanism. So we have two mechanisms: high index or modified total internal reflection, or low index, or in other words, photonic bandgap guiding. How the fibers are being manufactured, so this is only schematically, it is very difficult to manufacture of the fibers. That is why they are very expensive. For example, if a telecommunication fiber, 1 meter, the cost of telecommunication fiber is few cents only. So special fibers for special applications, not photonic crystal fibers, by, for example, which can maintain polarization, the costs are few dollars a meter. These fibers, photonic crystal fibers, can reach the price hundreds of dollars a meter. Due to the fact that technology process is very complicated and very costly, and it's not easy to achieve these fibers. So, although the fibers are no more than 1 decade, even 15 years, some of them, so still the prices are relatively high due to the technological process, complicated technological process. As you can see, we can distinguish these two types: low index of bandgap, or high index of modified total refraction, and different types of the fibers. They are very useful to interact with a nonlinear medium. So the glass can also act as a nonlinear medium. So in specific applications, we can obtain, due to these fibers, a guiding of a supercontinuum, so all frequencies in a high power. And they are commercially available devices, which is cost of about $30,000 each, which can be a source of a supercontinuum, of a source of a light. So it will be a source of a future light when the price goes down. Now about fundamentals of liquid crystals. We know about photonic crystal fibers and liquid crystals. I will just start a few minutes and then we'll make a break and we'll continue after the break. Liquid crystals have been first time mentioned by two people, German physicist Otto Lehmann and Austrian botanist Fritz Reinitzer in 1888. And as a matter of fact, the very first liquid crystal, so-called blue phase, was, as a matter of fact, photonic crystal. We know description because it have a photonic bandgap, stop bandgaps. So from these 2 days description, we can call liquid crystals as photonic crystals. And for these materials were granted Nobel Prize in Physics for Eugene, 1991. And standard, one of the most from applications point of view, they are so-called thermotropic liquid crystals, which can change their properties due to temperature. When you have a solid crystal and we just heat the solid crystal, standard crystal, not all the crystals, but specific type of solid crystals, we can melt, and we observe between normal or isotropic liquid and crystal, standard crystal, we can observe phases which are liquid phases but possess ordering characteristics for crystals. So that is why these phases are called, due to these inventors of liquid crystals, are called liquid crystal phases, or in other words, mesophases. Meso, so the phases between crystal and liquid. So the most important thing, these possess high anisotropy. Anisotropy as crystals, but they are liquid, so they can adopt the shape of the container, and they are practical in applications. Applications came only in the 60s, about 50 years ago, in watches, calculators, but in today's lab we have a laptop slab panel due to technology of liquid crystals. So the increase of applications in the last few years is enormous in liquid crystals. And one of the most important characteristics from the optical point of view is that the liquid crystals compose generally of elongated molecules. There are of course different types of liquid crystals, but we are interested only in liquid crystals composed of elongated molecules. And these elongated molecules, the dimensions of the molecules in the micro scale is about 1 nanometer long, and in comparison of the long axis and short axis is in most substances 10 to 1. So 1 nanometer and 0.1 nanometer typical. Of course there are differences. And when we discuss optical properties, the refractive index of light, extraordinary refractive index of light, is related to the long molecular axis. However, the ordinary index of light is related to the short molecular axis, and of course there is no difference. We can have 2 axes, x and y directions. As in classical crystals description, this is typical. They form beautiful pictures, phases. Some you can find in Google's internet. I just searched and found that the phases of liquid crystals are very beautiful, and you can observe beautiful pictures while observing under cross-polarized microscope. And for example, they can form disclinations line, and this is a nematic observed under polarized microscopes. So you can have, there's one of the book, Beauty of Liquid Crystals, and you can find a lot of beautiful pictures. Also some of them are available in the internet. As we heat a crystal, so it's a model of heating of heat, we observe phase transitions. So we observe a change of phases, and this view graph can be observed under polarizing microscope, cross-polarizers. And of course, there is a possibility, depending on material, that we can have a lot of phases. And when we reach the isotropic phase, the picture will be black due to the fact that this isotropic material under cross-polarizers is black. So some characteristics of basic thermotropic liquid crystals. So as I said, nematic liquid crystals composed of elongated molecules 10 to 1, so 1 nanometer to 0.1 nanometer. Chemical structure, most of them in the chemical structure have benzene rings. And these benzene rings are responsible for the diamagnetic properties of these materials. And this, due to the fact they are rigid, so the chemical structure is also rigid. And we have alternating chains which are flexible, but the core structure is rigid. There are, of course, different types, smectics, so the molecules are oriented within the layers, so they are, well, majority of smectic types of liquid crystals. They can be tilted as well. And these liquid crystals subjected to the either to the external fields or to the container, so to the glass container, can be deformed. So this is a deformation, so they can in space change the relative orientation of the molecules. One of the most important features of liquid crystals that in space these elongated molecules are parallel one to another, and this deformation is continuous. Deformation is continuous. To describe properties of liquid crystals, we can enumerate a lot of anisotropic properties. Nearly all the physical parameters are anisotropic. From our point of view, the most important anisotropies are dielectric anisotropy, optical anisotropy, and magnetic anisotropy. And a few words about each of them. Dielectric anisotropy relies, when we describe in the diagonal tensor, then we have also two dielectric constants for each liquid crystal material. One constant, epsilon parallel, when we measure the dielectric constants along the long molecular axis. And another constant perpendicular, so in this description, tensorial description, we'll have x, y, and z axis. So these two parameters are very important, and in general, in most liquid crystals, the dielectric constants along the parallel to the long molecular axis are greater than the perpendicular, but there are also cases that is vice versa. So there are two possibilities. Also, these electric dielectric constants are frequency dependent. So by changing the frequency of the electric field, we can change the relations between these two parameters. Free energy of deformation. Due to the fact that we can deform liquid crystals, there is a theory of elasticity developed in late 50s by Frank and co-workers, and they arrived at one of the most important formulas for liquid crystals, which is responsible for a majority of applications of liquid crystals. And this formula gives us the idea about free energy density, so-called Frank free energy density, which is split into three parameters. Three types of deformations. So we can have a deformations due to splay, which is responsible for K11 parameter. So it's the splay when we observe the molecules are going from a point and form a kind of a splay deformation. And this is a field, director field, which represents mean molecular orientation. Another deformation responsible for K22 parameter is twist. When we have molecules parallel oriented within the planes, and these plates are being continuously twisted. So this is a twist. And third type of deformation is related to the bend, K3-free, when we have molecules and we bend like a bulk material. So in general, all the deformations can be decomposed within these three deformations in liquid crystals. So another important anisotropical property is magnetic anisotropic properties. Also, we have two parameters which describe this structure: magnetic susceptibility parallel to the long polar axis and perpendicular. And this anisotropy, magnetic anisotropy, is positive in mostly materials, liquid crystal materials, due to the fact that this is greater than perpendicular. How this will influence when we put liquid crystals into the external field, either magnetic or electric field. So the field will interact, will reorient the liquid crystal, and this reorientation depends on the anisotropy, either magnetic anisotropy or dielectric anisotropy, delta T and delta epsilon. And this is a formula for the free energy density of interaction of pneumatic liquid crystals with external field. And this is responsible when we have a positive magnetic anisotropy, which is the case. In order to minimize this free energy, formula for free energy, this term should be maximal. So it means the magnetic field reorient parallel the molecules. So under magnetic field, molecules will be oriented parallel. Whereas in the electric field, it depends on the side of the electric anisotropy. With positive anisotropy, orientation will be parallel. However, with negative, will be perpendicular. And with a dielectric anisotropy is related optical anisotropy, so-called birefringence of the material. It is this extraordinary refractive index related to the parallel dielectric constants, but you have to just think that this dielectric constants is at optical frequencies. Optical frequencies is 10 to 15 power hertz. And that is why at these frequencies, this parameter is always higher than the perpendicular. It means that the anisotropy is positive. So birefringence of liquid crystals is positive, and this value of birefringence can be relatively high. Typically, birefringence is 0.2, but in the so-called high birefringence material, it can reach even the value of 1. That is an example of very well-known. I think we can make a short break, and we'll continue after the break. Okay?
Yeah.
Are there questions to the first part of the lecture? Yes.
I don't understand how the radial configuration can be stable. Always the defect should escape, no, to the axial configuration.
Axial configuration is stable with a boundary conditions perpendicular. Radial is not stable.
Yeah, radial is not stable.
You are right. So it's very difficult to achieve radial configuration. So very small distortion will just switch radial to axial configuration. You're right.
Are there more questions? If not, let us take our speaker.
this is greater than the setting threshold value. And normally, in normal situation, this effect would never occur. But due to fluctuations of the molecular orientation, this is a collective phenomenon which occurs, and the value of the threshold field is a very important parameter to characterize the liquid crystal sample or liquid crystal fiber. So this is a description. I would just not to go into details, some configurations, but the main idea as it follows. One of the most important from optical point of view liquid crystals are the liquid crystals called chiral nematic liquid crystals, or traditionally also cholesteric liquid crystals. This is, as a matter of fact, the first ever discovered phase in the 19th century by Lehmann and Reinitzer. However, this is described that we have a nematic liquid crystal in the layers, but the orientation of these layers is being continuously changing. And this special period of the changes is called helix, and this is characterized by the parameter which is responsible, P, pitch so-called, which is responsible for the 2-pi change of the orientation. Of course, from the optical point of view, important is only half of the pitch, because we cannot differentiate the just orientation into right or to left of the molecules. And these chiral nematic liquid crystals can form, this pitch can be measured in various methods. One of these methods is to put into the such a configuration, it is called Grandjean-Cano cell, and observe distribution deformations of this molecular orientation and measure the pitch. To demonstrate optical anisotropy of the liquid crystal, we can state, as it was told, that we have this ordinary refractive index and extraordinary refractive index when the light is polarized perpendicular to the non-molecular axis, ordinary, and parallel extraordinary. And when we have a tilted molecules, so the direction of tilted molecules, we can have an effective refractive index, so we can modify the bias of the medium due to the fact that the tilted configuration, the effective refractive index is described on the following formula. The most important feature, that is the optical anisotropy, strongly depends on temperature. And also not only optical anisotropy, but all the anisotropies are temperature dependent. When we have, this is one of the possible runs of the optical anisotropy, when we have extraordinary and ordinary refractive index, and from this side is a solid crystal, so crystal, and here's liquid crystalline phase, and at the temperature from the transition from liquid crystal to isotropic, this anisotropy will go to 0. That is why the material will become isotropic again. And this optical anisotropy strongly depends on temperature. That is why optical properties of liquid crystals depend on temperature. And with dielectric anisotropy, when we have a positive dielectric anisotropy, is delta epsilon greater than 0, we can reorient within the external electric field molecules along the electrical field. However, when we have a negative dielectric anisotropy, this reorientation will be perpendicular to the external electric field. And this is important for practical reasons, because we can influence by just using external electrical field, we can reorient the molecules within the devices, within the liquid crystal fibers as well. due to different types of anisotropies. And now let's go to the photonic liquid crystal fibers, as we call it. In the literature, it is also called liquid crystal infiltrated photonic crystal fibers. The name is relatively long, so that's why to shorten the name, we have proposed a few years ago the name photonic liquid crystal fibers, PLCFs. So, we take photonic crystal fibers. So we have structures which have both high index and low index guiding, modified total antenna reflection or photonic bandgap guiding. We have in our field of interest variety of different types of structures which can change with the dimensions of the holes, birefringence, and so on. And by adding to this photonic crystal fibers liquid crystals, we have a variety of physical phenomena, physical properties, a lot of different types of materials, and we merge both these structures. So in this sense, we obtain what we call photonic liquid crystal fibers. That is the topic of this set of lectures. And due to the fact that the structures merge the properties and advantages of both these different groups of fibers and liquid crystals, we can obtain a very high level of tunability of their propagation and polarization properties. So these structures, photonic liquid crystal fibers, can be very easily influenced, if we want, of course, by external electric, magnetic field temperature, pressure, and of course we can detect or we can play with polarization properties of these fibers. So we can have devices which can serve as a sensors, but also switches in configuration of optical fibers. So they can be not only sensors, but can be in-line fiber switches. What is the guiding mechanism in the photonic liquid crystal fibers? Will be the same as in photonic crystal fibers or different? Let us discuss it. When we have an empty, so the photonic crystal fibers itself, and we have the fiber with a solid core. So we have a refractive index of the core higher than the cladding, effective cladding. We have modified total antenna reflection, and we infiltrate the holes with liquid crystal. So this is liquid crystal. This yellow traces is liquid crystals. And we change the guiding mechanism. Why? Because when we infiltrate, mostly liquid crystals have refractive index higher than silica glass. So we enhance the refractive index than silica glass. So we reverse the mechanism of guiding. From pure photonic crystal fiber with total antenna reflection, we obtain the fiber with photonic bandgap. So we can reverse the index profile. So the core, glass core, will be lower than the average cladding. And of course, we can influence this mechanism by orientation of liquid crystals, as it was at the very beginning of this talk when we discussed these three structures. The planar is the most stable, and it is natural when we introduce liquid crystals, because liquid crystals are oriented generally by flow. So this is the most probable configuration. Axial is always also possible when we put a special treatment on the glass walls. And radial is possible but not stable, as it was the question. So, and due to these three mechanisms, we can change the profile of refractive index. So by influencing of orientation of liquid crystals, we can also change the guiding mechanism. So it is also very useful phenomena to switch. For example, if we start with planar orientation, infiltrate the liquid crystals which have ordinary refractive index lower than silica glass, and we will switch to axial, so this is the effective index will increase, and in the case of radial will be higher, so we switch from the total antenna reflection to the photonic bandgap guiding, only due to interaction with the walls. First ever demonstration of the propagation in photonic liquid crystal fibers was made not longer than 6 years ago, 2003. And it was obtained by the putting into the holes short pitch cholesteric liquid crystals, or chironematic liquid crystals. And by switching with temperature, by changing temperature, it was obtained thermo-optical tuning. So the light was tuned, the wavelength of the light was tuned due to the temperature. And in the nematic to isotropic phase transition, it disappeared. So it was 2003, and 2003 is the year when the photonic liquid crystal started. Since that, there were about more than 100 papers and publications on this topic throughout the world. And they were groups from Denmark, from US, from UK, and also our group. We have been doing relatively a lot of research in photonic liquid crystal fibers. This is the influence of electric field, so to switch properties, to tune the properties, optical properties, due to the electrical field, due to the fact that the field interacts, electric field interacts with the molecules. And this was the first demonstration in 2004, electro-optical tuning. There was also a demonstration of opto-optical tuning. And this is due to non-linear interaction. These interactions were enhanced by putting special dyes within the liquid crystal mixture which infiltrated the fiber. And these dyes can lower the threshold value of the optical field to reorient the structure. This is called opto-optical tuning. This is thermal tuning, which was observed by our group 3 years ago within a specific type of photonic liquid crystal fiber. This, due to the putting temperature, changing temperature, we could obtain a changing of the guiding mechanism within one of the single fiber. Let us observe, these are real pictures from the output of the fiber, and the photonic crystal fiber with a solid core was infiltrated with liquid crystals, so liquid crystals infiltrated these holes. And this is by heating, the second by heating, so we heat the fiber, we tune the wavelength, and rapidly we arrive to the situation that there is no propagation. So propagation disappears. And after increasing the fiber, propagation, increasing temperature within the fiber, propagation reappears, but different mechanism. This mechanism is total internal reflection. However, this is photonic bandgap. We'll see this in the next view graph. So, and this animation which represents the situation. So we have a photonic bandgap, then we reach the temperature when there is no propagation, and we have an index guiding or modified total internal reflection. Why is it possible? It was possible due to the fact that a special type of liquid crystals was chosen. And this is a liquid crystal. This is a liquid crystals which have ordinary refractive index, very low. extremely low. So the level of this refractive index is about a silica glass. This is a silica glass level, and this refractive index behaves ordinarily that in certain region of temperature is higher than silica glass, so above this threshold temperature is lower. So, and due to the fact that the molecules were oriented parallel to so we have a planar orientation, the propagation is being observed by this ordinary refractive index, and here will be photonic bandgap, and here will be total internal reflection. So this was demonstration of switching of the guiding mechanism due to the applications of very low birefringence liquid crystals, which is not trivial to obtain. And as a matter of fact, this material called 1550 is composed as a mixture of specific types of liquid crystals. As you can see, the birefringence of these materials is very low. So it is called low birefringence liquid crystals, and the mixture was synthesized at the collaborating groups of military university technology in Poland, and is not commercially available, so it's only a prototype mixture. So the question of alignment, so very important question. As you can see, the alignment played a predominant role in propagation mechanisms within these structures. Due to the fact that nematics are composed of these elongated molecules, and they tend to be oriented along the field, we have a possibilities of orientation within the tiny holes surrounding, within the photonic crystal fiber surrounding the silica glass core. One important thing is why we are using photonic crystal fibers is that we use only photonic crystal fibers with solid core. So the light will be propagated in a glass, but the propagation is influenced by the presence of liquid crystals surrounding the glass core. And that is why we can lower the attenuation, because propagation is not in a liquid crystals, as it was in the first liquid crystal core fibers, but propagation is in the silica glass, so in a glass. And presence of liquid crystals modifies only propagation. As you can see, these three types of orientations, planar, axial, and radial, are, as a matter of fact, so-called isotropic molecular orientation, because they do not change the symmetry of the medium. So this is always the fiber will become isotropic. The problem is how to change how to change from isotropic to anisotropic to plane, and how this rotation is important. So it can be changed due to the presence, for example, of external field above the Fredericks transition. So if we apply the field above the Fredericks transition, we can change this orientation, each of these orientation, into the so-called transverse orientation. So we can, this is the effect of vice versa, so reciprocal effect, that the initial planar orientation will become transverse under the external field, and vice versa. So the problem is how to put the conditions, this theoretical model, how to achieve this perfect orientation within these tiny holes, small holes. It is not easy, because in this place we have a possibility to put special substances on the cover glasses, and how to put substances within these holes, and the diameters of holes is about few microns. So it is important. It is important, but also very difficult to put. So one of the methods which can be used for this alignment is alignment due to light. So the method of photo alignment. And in context, the idea by applying ultraviolet light to specific polymers, azo-containing polymers and monolayers, and these, due to the transitions, so-called cis-trans isomerization transition of azo-benzene, can flip the position of these molecules and will reorient the molecules. So this method is relatively good when we produce displays devices, but has never been used so far to orient molecules within the fibers and photonic crystal fibers. So we have started 2 years ago to use some initial materials, polyvinyl cinemaide materials, for this type of orientation, and this is still in progress. So we are still doing a lot of research. One of the topic of our group is to use linear polarized UV light to make this reorientation and to obtain the molecules. I will not go to details into chemistry, but this will be used by the linear polarized light. How is the technology? Technology is rather complicated. Sometimes takes a few days or even weeks. But the idea is that we have a photonic crystal fiber, and first we fill these photonic crystal fibers with this solution. So as schematically drawn here, it's photonic crystal fibers, and we fill with this solution by using the external high pressure pump. Then we have to empty this fiber to achieve this small layer inside the holes, and it takes also a few hours or even a few days to relatively empty this long fiber, because in microscopic scale. Then we have to dry the fiber and have it cured for a certain time, and then when we have this solution, we have to irradiate with linear polarized UV light. Either parallel, the polarization will be either parallel to the long axis or perpendicular. So direction of polarization of the light is responsible for orientation. So either we'll achieve axial radial orientation, or we will achieve the planar orientation. So the direction of orientation of UV linear polarized light, it must be, of course, ultraviolet, because it enables cross-linking of transformation, isomerization. And once this is done, we can only infiltrate with liquid crystal. And these liquid crystal molecules will follow the orientation of the layers, PVCI layers, oriented by the linear polarized light. And now there are some examples. These are examples of obtaining orientation from real fibers. From the very beginning, of course, we used capillaries, so separate fibers, not photonic crystal fibers, because it would be difficult to observe the phenomena. But later on, we have been using also photonic crystal fibers. So both orientation, perpendicular and parallel orientations have been used. This is a capillary with a typical 5 cb liquid crystals and the cross-polarized. So two sections, specificator of two types of orientations, and demonstration that two sections are either perpendicular or parallel to this orientation. These are not oriented as, to mask them and to demonstrate the orientation. And the observation under microscope, this perpendicular orientation. So this is the kitchen, how to achieve this photo orientation, photo alignment, and this is a rotation of the sample which demonstrates level of these oriented substances so within the one capillary. Some experimental results with photoorientation. So, as a typical material, photonic crystal material, which have been used to infiltrate with the liquid crystals, is a material isotropic photonic crystal fiber manufactured at the collaborating university, Maria Klitschkowska University, and the structure is the hole diameters, small hole diameters in this level less than 5 microns, and spacing of the holes is 6.5 microns. So with this isotropic material, we have infiltrated different types of liquid crystals. These are typical liquid crystals with typical birefringence on the level of 0.2. And this is an animation from the experiment with the influence of alignment to the properties of this material. So by rotating, angular rotation, we can have obtained a demonstration of photoorientation results. When we have a parallel orientation, and by introducing specific type materials, we can also switch propagation from the solid core glass to the liquid crystal cores within the holes. And this is kind of can serve as also nonlinear effect. So we can obtain a structure which will be multi-core fiber guided within these liquid crystal holes. And this is how the electrical field influences the oriented sample. So this switches from the planar to transverse orientation. So we observe a voltage which has been applied across the fiber, and this voltage influences the possibilities, the propagation wavelengths of the fiber. And this is the answer why we are using these fibers, photonic liquid fibers. We can influence propagation properties, and we can also switch propagation properties. So it's another type of orientation. So the orientation with perpendicular and tuning with electrical field with photoline sample. So it is with the negative optical anisotropic material in order to tune this. As you can see, we can tune not only the power, but we can also tune the wavelengths. Different band gaps appear, so different wavelengths are being guided within the fiber. Photonic liquid crystal fiber components. What are the components which can be used to manufacture photonic liquid crystal fibers? So we can use also commercially available. So two types, apart of these isotropic fibers, we can have also as a components birefringent or anisotropic fiber. These fibers are being manufactured by the company Blaze Photonics and Crystal Fiber, and the parameters. So this is a highly birefringent fiber. The parameters of the fiber are that the not whole cladding is composed with holes, but also we have small holes and big holes. And big holes can define an axis of birefringence. The same is in the second fiber. And these are isotropic photonic crystal fibers, different types of isotropic, manufactured at the university, not commercially available. And the level of rings is responsible for the properties. The lower the level of rings, the influence of liquid crystals which infiltrate will be lower, because the level, of course, the number of rings and also the dimensions of rings are very important. These are these fibers which were used for thermal tuning of guiding mechanism. And this is a totally new fiber, which I will discuss on Friday, which is a high index glass. So the index will be enhanced in comparison to silica glass, because these are made from silica glass and this high index glass. As you can see, this is a fiber with low holes but with a high index. And the index can achieve even the value of 1.6, 1.7. And the materials, we can infiltrate the fibers with different type of liquid crystal materials. These are standard liquid crystal materials which are commercially available. One of well-known liquid crystal, 5CB or PCB sometimes, pentylocyanobiphenols, is the most popular liquid crystal material ever used and ever described. And the composition is, as you can see here, two benzene rings, so biphenyl rings, CN group and C5H11 alkyl chain. And similar to this is a S6S8BT. These materials are characterized by the typical for liquid crystals birefringence at the level of 0.2, and the running, they are both refractive indices are higher than the silica glass. This is silica glass, and these are both. So we call these materials medium birefringence materials. However, we have also in possession low birefringence prototype materials, which can serve to switch the guiding mechanism within liquid crystals. So first material is ever manufactured is 1110, but the better material is 1550, the material which have a greater difference of the refractive indices in comparison to 1110. And presently we have synthesized material which is much better. It is, we call it 1800, because it starts at room temperature with the lower refractive index than silica glass. So this material, this mixture, because it's a mixture of a group of materials, is so far not published, submitted to publications, so it's very interesting, and we are doing research with these materials. So these are low birefringence materials. We can use also, from another side, very high birefringence materials. And the group of materials starts double the standard birefringence. So you can see it reaches 0.4 or even higher. And these materials are specifically good to be influenced by external electrical field. So because have the nice dielectric anisotropy, very high dielectric anisotropy, so it means they will be easily influenced or powered by electrical field. I think I will skip today anisotropic highly birefringent fiber. How many minutes do we have?
Fine, but you could go.
Yeah, okay, because I will discuss this in details. So on Friday it's a very important issue. So I will go to the further. We will start from sensors, okay. So one of the first applications of photonic liquid crystal fiber are sensors. And first of all, a sensor of electrical field, because it can change propagation properties. The fiber itself change propagation properties within electrical field. When we have the commercially available fiber with these two big holes, and we infiltrate with these big holes with liquid crystal, we can do it only separately, not the whole issue, whole stuff, but on these big holes. And we can switch the orientation of the molecules within these big holes with electrical fields. So in that sense, we can obtain a sensor which can be a threshold sensor, because which reacts very rapidly for a threshold voltage for different wavelengths, so operating at different wavelengths. So one, it can be electrical field threshold sensors. And this can be observed also because it influences the polarization. And the polarization can be represented on the Poincare sphere. On polarization, on Friday, we'll deal much more. So this is only the results, how this polarization is observed under influence of the on the Poincare sphere with the electrical field. Another possibility is to build a hydrostatic pressure sensor, which we have done 2 years ago and still will be continued. And we put this fiber into high pressure environment, and the pressure changes the propagation and also polarization properties. Stresses, this is schematically drawn how the pressure influences the polarization, propagation properties of within when this is put to the high pressure chamber. And this is very interesting because when we have just the propagation, we have two band gaps, but large band gaps, and the hydrostatic pressure will narrow the width of the band gaps. So only one side narrowing effect. So this can be also used for very sensitive pressure sensing, but the effect itself is very interesting, and the investigation are still in progress. So narrowing effect is relatively large, and this narrowing effect, one side narrowing effect, can be useful to calculate phase birefringence pressure sensitivity. So parameter which is characteristic for the hydrostatic pressure sensor. And the fiber itself can be used in telecommunication. So the fiber, when we put the liquid crystals into, for example, two big holes separately, it can be used in telecommunication for dynamic depolarization compensation. The problem very important in fiber optic telecommunication, PMD, polarization mode dispersion. The people are looking for reliable devices which can compensate this depolarization effect, and this fiber, when put into electrical field, can be dynamic compensator. So this can be addressed, of course, later on Friday. Some of the devices which we have constructed within this European Network of Excellence, demonstrator of temperature and electrical field, so devices within the photonic liquid fibers. So I will show you the results of these devices, and we have chosen the fibers, this type of photonic crystal fibers, and the liquid crystals to infiltrate. So as you can see, with medium birefringence and with low birefringence. And these were devices which were powered by supercontinuum, so the whole spectrum. This is very expensive, but it can be also commercially available supercontinuous source based by photonic crystal fiber. And this is a device because we have a pigtail fiber, we have a switch, just connector, and the device itself is here. So photonic liquid crystal fiber, small piece of fiber, which is put this kind of demonstrator, especially with a plate with a P-Rafs with a module to have a possibility to heat the fiber, but also to apply the electrical field. So this is electrodes, and it's a real device. And the results for different types of rings. So we have been investigating, characterizing devices for wavelengths and temperatures, and the results for length of the device is 1.5 centimeter, and only 3 rings were infiltrated with the medium birefringence liquid crystal. So these are characteristics of thermal characteristics. So as you can see, by choosing different types of liquid crystals, we can change the scale of application. So the device demonstrator can be sensitive to different types of ranges of temperature. The same with electrical field. We can characterize for different wavelengths and voltages applied across the fiber, and this can be by choosing appropriate liquid crystals. This can be a threshold value device or threshold field characteristic, or even a type of sensor, so for which will be sensed for different wavelengths. So these are not commercial available devices, but demonstrators which still are working and can be seen in our lab. Last topic of today, few graphs, that the fibers, photonic nucleus fibers, possess also high nonlinear properties. Due to the fact that liquid crystals are nonlinear material, so by making experiment with a high power laser, titanium sapphire laser, we can observe opto-optical switching and opto-optical coupling. As you can see here, by increasing power, this is data from experiment, we can obtain modification of refractive index of liquid crystals, and the initial light which is being contained in the core can spread within the liquid crystals, which will have the higher modified by optical field refractive index. So this is a demonstration results from 2007, and still our works are in progress, of the nonlinear performance of the liquid crystal. So this is another branch of activities of applications, to have the devices which will be modified by optical field, not by electrical field, by optical field. So to sum up, the photonic liquid crystal fibers can be modified their properties, tune their properties by temperature, electrical field, but also by optical field of the light wave. And different tunable mechanisms are possible and have been so far demonstrated. This mechanism, this tunable mechanism, can be dynamically tuned, so we can have the reciprocal effects. So when we apply the field, we have a switching or tunability possibility. We remove the field, so that is why we can have a multi-parameter fiber optic sensors of different parameters. We can have devices or methods for optical processor and optical processing and dynamic telecom devices. On Friday, I will keep your attention mostly on beautiful polarization properties, and also on other applications on photonic liquid crystal fibers. So they offer us a lot of new opportunities, and this topic to be continued, I believe. Thank you very much.
Questions, please? I have a question. So the losses, light losses in the liquid crystal medium, as you mentioned, at quite high. From this point of view, can you have like partially infiltrated photonic crystal fiber so that you could simply use this portion for tunability?
Very good question. So I will present on Friday the devices we have constructed when we have a photonic crystal fiber and one short section was infiltrated. So it's a very good question. So I just skipped this part today. But of course, in order to diminish losses, that is why we try to propagate the light in solid core, in glass core, and liquid crystal only change properties. And that is why we lower, because when it started 10 years ago, so we have propagation in liquid crystal core and the losses were very high. So we could propagate only very few centimeters and the light disappeared. Now we have a possibility to propagate for long distances. We demonstrated propagation for some meter scale. But still, for tuning and for processing, it is better to have short section. It will be enough because we change properties. Very good question. So I will just please keep your attention on Friday on this specific type of devices.
Are there more questions? Yes.
I have a question about the fiber for sensing. There are two band gap in the system, but the bandwidth of one band gap is unchanged, but the other is become narrow when the pressure is changed. So could you give me some explanation about this phenomenon?
Yeah. So one band gap really in high pressure sensor, one band was unchanged, and this other band gap was dominated over the first band gap. So, and we don't know up to the day why we observe narrowing effect only for one side. So the pressure influence is much more complicated than the temperature or electrical field. This is only phenomenological observation. And the explanation why is so far we don't know, because it involves the whole theory of elasticity of solids but also fluids, because pressure changes dimensions. And the response is not so simple as in the temperature method. So it's only observation. So it's only observation, basic observation. And the whole theoretical approach should be undertaken. But that's a good question.
Are there more questions? If not, let us thank our speakers. So I just want to make a quick announcement that tomorrow during the afternoon session we will move